Hello, good evening everyone. Myself Pradeev E, I am one of the TA for this course on ice engines and gas turbines in NPTEL. Today I will go through the concepts of intercooling regeneration and reheating for gas turbines. So on last week we had some problems on standard Brayton cycle, and now we will see some additional concepts for the Brayton cycle. So participants can mute yourself. When you have questions, you can unmute and ask. Thank you. So first we will see intercooling. Generally, the Brayton cycle or the gas turbine cycle starts with a compressor, and in case of intercooling, there are two compressors. And then we have a combustion chamber, and then this is get to the turbine, and then this goes out. So this is called intercooler. Assume the pressure ratio represented as RP is initially 9. That means P2 by P1 was 9 from the standard Brayton cycle. So now we will split this pressure ratio into in two compressors, and this can be like RP1 is 3 and then RP2 is another 3. And we will have an intercooler, so that will reduce the temperature at the outlet of the compressor 1, and because of this we will achieve some lower compression work. So if you want to plot this process in PV diagram, generally if you start a compression work from here, from this point, then compressors like this for a isentropic process. And since it is a flow machine, we say the work done is V into dP. If you haven't, so that means this entire region will be the work done for a general compressor. Now if you want to cool down, assume after so this is P1 and this is P2. After P2 dash we are taking to an intercooler where we are cooling down. Then that means at constant pressure you will reduce the temperature. Then that means the specific volume will decrease, and on this PV plot you will see a horizontal line for representing the intercooler process. And then after that we will compress it to the second pressure level P2. Then it goes like this. So initially you had this region, and now this overlapping region is avoided in compression. So that means now the revised compression work will be only this, will be represented by this area. So this is the advantage of using an intercooler. Similarly, when you have regeneration, instead of directly going to a combustion chamber, first it goes to a heat exchanger. So assume this is 1, 2, 3, 4 and 5, representing this in TS diagram. First the compression 1 to 2 is a isentropic compression, so that will be represented by a vertical line 1 to 2, and then constant pressure heat rejection is 2 to 3, sorry, heat addition, so that will increase the increase the temperature and entropy like this, since it is a constant pressure. On the TS plot it is a curve, and then again with the, so this is 2 bar, and then we reach 3 this is 3, and then this is 4. So initial few heating is done by the regenerating heat exchanger. And then the other process are the same. Now if you see the heating, earlier it would be H4 minus H2, but now it is H4 minus H3. Here you can see the effectiveness of the system. Okay, I think that effectiveness we will go through the problem. Now in reheating, the expansion is done at 2 stages. So we have a combustion chamber, and then there is a first turbine, and then there is another combustion chamber, and then you have turbine 2.
Excuse me, sir.
Yes.
Excuse me.
Yes.
Okay. In regeneration process, that Q regeneration should be H3 minus H2, right?
H3 minus H2. No, H3 and 2, across 3 and 2 it is from the heat exchanger. So Q that is supplied by the external agency, like a fuel, that is what I have written. So earlier it was the whole heat was supplied by the combustion chamber itself. Now it is only H3 minus H4.
Oh, okay. That is it. Okay.
This is Q heat input. Okay. So in this, with reheating, for compression, assume this 1, 2, 3, 4, 5 and 6. Initial compression happens at constant entropy, and then this combustion chamber adds the heat at constant pressure, something like this, and then we will have a first expansion, and then we have the second combustion chamber. So this is 1, 2 and 3. So after the heat addition, we end up in 3, and then after turbine 1 we end up in 4 through a constant entropy expansion, and then again the second combustion chamber heats up like this, and then goes, and then so this is 4, 5 and 6. So these are the different process in which the efficiency of the base Brayton cycle can be improved. I hope this will be clear, because the same thing will be taught in the video also. I just want to brush up this basic so that when we go to the problems it is easier. So in the first problem, we have to determine the specific work output, specific fuel consumption and cycle efficiency of a heat exchange cycle as shown in the figure. So this is a regeneration cycle. And having the following specification: compressor pressure ratio is given as 4.0, turbine inlet temperature is 1100 Kelvin, isentropic efficiency of the compressor is given, isentropic efficiency of turbine is also given, mechanical transmission loss is given. So that means if 100 joules of mechanical work is produced by the turbine, only 99 joules can go into the compressor. The remaining 1 joule will be lost as friction into the atmosphere. And combustion efficiency is given as 0.98. So this means out of 100 joules of fuel energy that is given in, only 98 joules is converted to as heat energy. 2 joules can be lost during as a heat transfer to the surrounding, or it can be as an unburnt fuel outside. So generally when combustion happens, that not all the fuel molecules that comes in will get combustion goes out. Sometimes a partial combustion can happen because of insufficient temperature or insufficient time for the combustion, and because of this we will have some carbon monoxide or hydrocarbon emissions coming out. So this will lead to combustion inefficiencies. And we have a heat exchanger effectiveness of 0.8, and pressure losses is given during across the combustion chamber. The loss is 2% of the delivery pressure, and across the heat exchanger air side it is 3%, and the heat exchanger gas side is 0.04%. So ambient condition is given as 1 bar and 288 Kelvin. We have to find specific work output, specific fuel consumption, and cycle efficiency. So we can start from the first point. So if you want to draw this in TS diagram, the first is the compressor. 1 to 2 is isentropic compression. The pressure ratio is given as 4.0. Then we have constant 2 to 5 is heat addition at constant pressure, and that pressure loss is also given. So it goes like this, 2 to 5, and then again there is another heat addition 5 to 3 given by fuel, and then we have expansion 3 to 4, and then 4 to 1 is so 4 to 1. In between 4 to 1 we have some 0.6, and then it comes down. So here the temperature, say T4, and this is T6, and here it is T2 and T5. Heat exchanger effectiveness is given as the maximum or the actual heat transfer by maximum heat transfer. So maximum heat transfer is when this temperature at the fourth point, while it exceeds the heat exchanger, reaches the temperature of the second state, that is T2. That means if T6 is equal to T2, what would be the heat transfer is what? The maximum theoretical heat transfer. So that can be mentioned as H4 minus H2, right? Here we consider H is always Cp into T, so all Cp's will get cancelled, and then we will have temperatures. And but actually we are having only H4 minus H6. So this is the effectiveness definition for the heat exchanger during regeneration cycle. And because of this we know T4 is T6 is greater than T2, but here we are not seen in the plot. The plot has to be plotted correctly, the TS diagram. Now we know the state at 1, so P1 is 1 bar, T1 is 288 Kelvin. I will keep on solving for the of all the points. So then later finally we can calculate the work output and the fuel consumption. So now we know that the pressure ratio is 1, from 1 to 2 is 4. With the pressure ratio we can calculate the temperature ratio, and mostly it is better to have this expression in mind, otherwise I would like to derive with this. So now we know during isentropic expansion or compression, we know PV power n or PV power gamma is equal to constant. So that means P1 V1 power gamma equal to P2 V2 power gamma. Now we know the pressure ratio P2 by P1, so that is V1 by V2 power gamma. Now we need to know the temperature ratio. So for temperature ratio we need to take the ideal gas equation PV equal to RT, which implies PV by T is equal to constant, or P1 V1 by T1 is equal to P2 V2 by T2. Now we know if you have V1 by V2 is equal to P2 by T2 into T1 by P1. Now I know what is V1 by V2. So here I can write V1 by V2 is P2 by P1 power 1 by gamma. Then I can relate equation 1 and 2. Then I would get P2 by P1 power 1 by gamma is equal to P2 by P1 into T1 by T2. So I write T2 by T1 is equal to, I would have P2 by P1 into P1 by P2 1 by gamma. This can be P2 by P1 into 1 minus 1 by gamma. So this is P2 by P1 power gamma minus 1 by gamma. This is T2 by T1. Now T2 is equal to T1 is known as 288 Kelvin and pressure ratio is known as 4, and then we have gamma minus 1.4 by 1.4. Okay, I think I used the calculator. Please solve this and I would get the calculator. I think there is some problem. I will restart the application. What happened?
Network is not working.
Oh, network only, yeah? Sure.
Yeah.
But then why?
It's disconnected in mine.
Then why this also gone?
No, mine is disconnected. It said you lost your network connection.
Oh, network.
And CC networks also is not working.
CC means?
CC networks means net access.
But why my this also closed and see only half came?
It hasn't loaded, man.
No. I wrote something. No.
Why you are telling again this one?
I don't remember the formula.
I'm downloading my gate scorecard and it's gone.
Okay, I will start again.
Now that they won't come. Got the connection?
Oh, no connection. Connection means I have to put transport.
Oh.
We'll have backup.
I don't have connection then. Why?
Sure that internet.
Yeah, mine is got disconnected.
Hello, sorry for the interruption. I think there are problems with the network. So now T2 is T1 into P2 by P1 power gamma minus 1 by gamma. T1 is given in the problem as 288 and pressure ratio is known as 4, and 1 minus gamma is 0.4, and then in the denominator for the exponent we have 0.4 by 1.4. Now T2 can be calculated. And it is 428 Kelvin. I think we will be told that there will be some losses. Yes, so the isentropic efficiency of the compressor is 85%. So whatever we have calculated will be the isentropic value, and now we need to have the actual temperature. So to find the actual temperature, we will have isentropic compressor efficiency is isentropic work by actual work. It is 0.85, and isentropic work is T2s minus T1, and actual work is T2 by T1. So here we generally write in terms of enthalpy, since we take Cp as constant and Cp get cancelled out, we will have only T which is left over. Now T2s is 428 Kelvin and minus T1 is 288 Kelvin, and T2 is unknown, and minus 288. So T2 is 428 minus 288 divided by 0.85 plus 288. So this is 452.7 Kelvin. So this is the outlet temperature of the compressor. Now so in this process we had, in the TS diagram we had something like this, and then we are told that the turbine inlet temperature is 1100 Kelvin. So that means T3 is 1100 Kelvin. But before that we have some heat addition. We have found the H2, and now we need to find H5. Right. So for H5, how do we calculate? Okay, I think from based on the turbine inlet condition, we can find the outlet temperature. So T4 can be calculated because we know the pressure ratio and the and also the pressure ratio and the inlet temperature. So that means here we have T3 by T4 is T3 by P4 power gamma minus 1 by gamma. Here T3 is 1100 Kelvin. So 1100 divided by T4 is equal to 4 power 0.4 by 1.4. So that means T4 is equal to 740.25 2 Kelvin, and this is the isentropic temperature. In actual we will have a different one. So writing the expression for the turbine isentropic efficiency, we have actual work by ideal isentropic work. So that is in actual we have T3 minus T4. In isentropic we have T3 minus T4s, and this isentropic efficiency is given as 0.87. Sorry, I think the computer got hanged. Hello. Sorry again for the interruption. There were after restarting the PC, now it is fine. So now we have this turbine efficiency as 0.87, which is actual work by ideal work. In actual case, we have the temperature T3 minus T4, and in ideal we have T3 minus T4s. So T3 is 1100, so that is given 1100 minus T4 is what we need to find. by again 1100 minus T4s is 740.2, and this is 0.87. So T4 can be calculated now. Which is 0.87 into 1100 minus 740.2 plus minus and plus 100, 1100. So this is 786.97 Kelvin. Actually, the turbine ratio, the pressure ratio for turbine is not actually 4, because there is some 2% and 3% drop in efficiency. So that means actually the turbine pressure ratio would be would be 0.98 into 0.97. So neglecting the loss, so remain the except the loss of 2% and 3%, only remaining will come through. So that means this into 4 would be the turbine expansion ratio. This is around 3.8024. This is the actual ratio, but I think we have started to solve with the pressure ratio of 4. Maybe we can do a next variation when we consider this pressure losses. Now we have found the value of T4. Now I think it will be, we will be able to find use the effectiveness value, because we have T4 minus T6 divided by again T4 minus T2. The value of T2 is known, right? Yes. Since the value of T2 is known, now we can actually find the value of T6. So the change in enthalpy in the heat exchanger can be found out, and then we can use that for calculating the enthalpy change between H2 and H5. So here across the heat exchanger, H4 minus H6 should be equal to H5 minus H2. So this can be used. So now using effectiveness, effectiveness is 0.8. So this 0.8 is equal to T4 is given, just now we have calculated 786.97 minus T6 is unknown, and again in the denominator 786.97 minus T2. T2 we have calculated as 452.7. So T6 is 0.8 into 786.97 minus 452.7. So my negation of this plus 786.97. So this is 519.5 Kelvin. So now we know the heat transfer to the heat exchanger, that is H4 minus H6. So Q heat exchanger is Cp into T, or we can directly write with the heat this one with the heat exchange being same across the streams, we will have T4 minus T6 equal to T5 minus T2. T5 minus T2. So T4 and 6 we have. T4 is 786.97 minus T6 is 519.5. This is equal to T5. T5 is unknown, but T2 is known. T2 is 442.7. So that means T5 that is 720.17 Kelvin. So now we know how much of heat has come from the heat exchanger and how much has come from the fuel. So with this we can calculate the specific fuel consumption of the fuel. So now specific work output is asked for. So work output is from here we have H4 minus H3. So I will write turbine work is H4 minus H3 and compressor work is H2 minus H1. And this is Cp into T4 minus T3, and this is Cp into T2 minus T1. So turbine work can be written as Cp is 1.005, T4 and T3 can be written. T4 is 786.97 minus T3 is 1100. Actually it should be T3 minus T4, so I would write a minus here. So then it will become (314.59 kilojoule per kg). This is turbine work. Similarly, compression work is Cp is 1.005 into T2 T2 is 452.7 minus T1 is 288. This is 165.5 kilojoule per kg. So specific work output is W turbine minus W compressor, which is 314.59 minus 165.5. That is 149.09 kilojoule per kg. So this is the specific work output. Similarly, specific fuel consumption and cycle efficiency can be calculated. So for specific fuel consumption, we need to know the enthalpy addition by the fuel, enthalpy addition by fuel is H3 minus H5, or I would put heat in is H3 minus H5, so that is 1.0, sorry, again it is Cp into T3 minus T5, so Cp is 1.005, T3 is 1100, and T5 is, just calculated, 720.17. This is 381.73 kilojoule per kg. This is heat that is added, but there is something called combustion efficiency which is given, so that is Q in by Q fuel, and this is combustion efficiency is given as 98%. So this is 0.98 is equal to 381.73 by Q fuel. So Q fuel can be calculated as 381.73 divided by 0.98. This is 389.52 kilojoule per kg. So this is a specific this is a fuel added, or heat energy that is added for 1 kg of the working fuel. Since we need a specific work output, specific fuel consumption, that is SFC is equal to generally the calorific value of the fuel will be given, and then the specific fuel consumption will be in terms of gram per kilowatt hour. So here watt hour is the mechanical energy and gram is the fuel mass that is used to produce 1 unit of the mechanical energy. But here this calorific value is not given, so then we cannot convert the mass. We don't have the relation between the fuel energy and the mass, so I think we can leave it like this. Then we need to calculate the cycle efficiency. So eta cycle equal to work output but by fuel input. So work output we have calculated as W net, that is 149.09, and fuel input we know it is 389.52. This is 38.27%. Do you have any questions with this problem? I will just go through it once. We need to calculate specific work output and specific fuel consumption and cycle efficiency of a heat exchange cycle. So the heat exchange the cycle schematic diagram is given within the problem itself. So point 1 denotes the inlet condition for the compressor, so that is also given as 1 bar and 288 Kelvin, and after the compressor, the isentropic efficiency is given as 0.85, and then the state 2, the outlet state of the compressor represented by 2 is fed into a heat exchanger, where gets heated and heat is added to at constant pressure to temperature of T5, and then fuel energy is added, then it becomes at constant pressure, and then it becomes state 3. From 3 it is expanded using a turbine, and then it is expanded to a state of 4. From 4 it is given to the heat exchanger, where it adds heat to the intake charge, and from 4 the outlet of the heat exchanger is represented by state 6. Now we haven't considered the pressure losses while solving this problem, but however we have considered the isentropic efficiency of the compressor and turbine, and also the combustion efficiency and heat exchanger effectiveness. Heat exchanger effectiveness is defined by the actual heat transfer to the maximum heat transfer. Actual heat transfer occurs between the temperature T4 and T6, that the actual temperature difference or the actual enthalpy difference. But maximum heat transfer is possible when the outlet temperature or outlet temperature of the heat exchanger becomes the inlet temperature of the air charge that enters in. So when when the outlet temperature, if the 6 has been equal to 2, like T6 is equal to T2, then we will have the maximum heat transfer. So that goes into the denominator of the effectiveness. Then with this we also know that T6 is greater than T2. Then effectiveness is given by T4 minus T6 by T4 minus T2. And also with the heat exchanger we know whatever energy that is given in by one stream will be the energy taken by the other stream. So with that H4 minus H6 is H5 minus H2. So this relation we use later, and we have started calculating using the isentropic expansion in the compression in the compressor with the initial temperature of 288 Kelvin for a pressure ratio of 4. We have found that the isentropic compressor out temperature is 428 Kelvin, but using isentropic efficiency of 85%, we found that the actual temperature outlet is 452.7 Kelvin. And similarly the turbine inlet temperature is given as 1100 Kelvin, and we assume the pressure ratio of 4, but actually we saw based on the losses it is around 3.804. But so we have started with assuming it at 4, so we continue with the problem like this, and we found that the isentropic temperature outlet of the turbine is 740.2 Kelvin, but in actual, using the efficiency of the turbine, we got it to be 786.97 Kelvin. Then actually the temperature outlet should be lower than the ideal case. Yeah, okay, fine. This is right. So that means delta enthalpy change for the ideal cases more than the actual case. So this is correct. Now we have we use the effectiveness equation for the heat exchanger, which is T4 minus T6 by T4 minus T2. With this we can calculate T6, which is 519.5 Kelvin, and that is outlet temperature of the air. And with the difference between T4 and T6, that is the hot side gas streams temperature difference, we can find the T5, that is the outlet temperature of the cold side of the heat exchanger, and that is found to be 720.17 Kelvin. Now we can calculate the turbine work and compression work because we know the inlet and outlet temperatures, and we have found the net work output as 149.09 kilojoule per kg, and heat in given by the combustion chamber through the fuel is also calculated by the enthalpy difference or the temperature difference across the combustion chamber. And using the combustion efficiency of 98%, we computed the actual fuel energy that has to go in, which is 389.52 kilojoule per kg yeah. And cycle efficiency can now be calculated because we have the work output and the fuel input, and it turned out to be 38.27%. I hope this problem is clear. If you have any questions with the problem, you can feel free to ask now. If there are no questions, then I will move on to the next problem. This problem is also much similar to what we saw earlier, so I will take the next problem. I think this is simpler than the one we see earlier. Brayton cycle with regeneration using air as the working fluid has a pressure ratio of 7. The minimum and maximum temperatures in the cycle are 310 and 1150 Kelvin. Assuming an isentropic efficiency of 75% of the compressor and 82% of the turbine, and an effectiveness of 65% for the regenerator, determine the air temperature at the turbine exit, the net work output, and the thermal efficiency. Only these three. Now drawing the TS diagram, we have the compression represented by a vertical line 1 to 2, and then it first goes to a regeneration and then actual heat input, and then we have say this is 3, and it expands and then heat is added till 4, and then it is expanded till 5, and then this is 6, so it goes like this. Now the lowest temperature is set at 310 Kelvin, so that is T1 is 310 Kelvin. Similarly, the maximum temperature is, which is T4, is 1150 Kelvin. Isentropic efficiency of the compressor eta C is 0.75, and that of the turbine is 0.82, and effectiveness of the heat exchanger is 0.65. Now T2 by T1 is P2 by P1 over gamma minus 1 by gamma. So T2 is T1 into pressure ratio power gamma minus 1 by gamma. So that is T1 is known, which is 310 Kelvin, into pressure ratio is 7, and gamma minus 1 by gamma is 0.4 by 1.4. So this is 540.5 Kelvin. And this is isentropic temperature, but actual temperature will be a little different based on the efficiency. So isentropic efficiency of the compressor is ideal work by actual work. That is T2 S minus T1 divided by T2 minus T1. Isentropic efficiency of the compressor is given as 0.75, which is T2S is 540.5 minus T1 is 310 Kelvin divided by T2 minus 310. So now T2 is 310 plus 540.5 minus 310 divided by 0.75. This is 617.3 Kelvin. And similarly, if you want to calculate the temperature at the outlet of the turbine, we have T4 by T5 is equal to P4 by P5 power gamma minus 1 by gamma. So T4 is known, which is 1150 divided by T5 is equal to this is pressure ratio. P4 by P5 is the pressure ratio, which is 4, and then we have to the power 1.4 power by 1.4 by 1.4. So now T5 is equal to 1150 divided by 4 power 0.4 by 1.4. So this is 773.9 Kelvin. Now we can use the effectiveness relation. Goes at 2 and comes out at 3. Similarly, comes at 5 and 6. So effectiveness is T5 minus T2 divided by T5 minus T4 divided by T5 minus T2. This is 0.65 equal to T5 is 773.9 minus T4. T4 is given in the problem as 1150 then this divided by T5 minus T2. T5 is 773.9 minus T2 is unknown. Now we can calculate T2, which is 773.9 minus 773.9 minus 1150. I think T4 is, I think this is 6. So then we have 0.65 is equal to T5 is 773.9 minus T6 is unknown divided by 773.9 minus T2. It's not actually T2, yeah, it's T2. T2 is 617.3. Now T6 is 773.9 minus 0.65 into 773.9 minus 617.3. This is 672.11 Kelvin. So T6 is found now, and with this we know what is the heat input. So Q heat exchanger is H5 minus H6, which will be equal to H3 minus H2. So this is T5 minus T6 is equal to T3 minus T2. So T5 is 773.9 and T6 is 672.11 is equal to T3 minus T2. T3 is unknown, T2 is known as (617.3 Kelvin). So now T3 672.11 minus 617.3 minus 773.9. So this is plus, this is 773.9 minus 672.11 plus 617.3. This is 719.09 Kelvin. This is the temperature at the inlet of the combustion chamber. Now temperature at the turbine exit is found. The air temperature Okay, and net work output has to be found. So turbine work is Cp into H4 minus H5, sorry, T4 minus T5. Similarly, compression work is Cp into T2 minus T1. So turbine work is 1.005 into T4 minus T5. T4 is given as 1150 minus T5 is so turbine work is T4 minus T5. T4 is known, T5 is 773.9. This is 378 kilojoule per kg. This is turbine work. Similarly, compression work is Cp into T2 minus T1. So this is 1.005 into T2 is so 617.3 minus T minus T1, which is T1 is given as 310 Kelvin. This is 308.84 kilojoule per kg. Now network output can be found, which is turbine work minus compression work, which is 378 minus 308.84. So this is roughly 70 kilojoule per kg. So we have found the work output, and next is the thermal efficiency. So for thermal efficiency, we need to find the Q, the input, and that is Q in is H4 minus H3, and H4 we know it is 1150 Kelvin minus H3. Sorry, or H3 or T3 is T3 is 719.09. So this into Cp. So that is 1.005 into this turns out to be 382.81 kilojoule per kg. And now if you want to calculate the cycle efficiency, which is work output by heat input, which is 70 divided by 382.81. This is 18.3%. Do you have any questions with this problem? If there are no questions, I will move on to the next problem. In this problem, we have a stationary gas turbine power plant which operates on an ideal regenerative Brayton cycle with effectiveness of 100% with air as working fluid. The air enters a compressor at 95 kilopascal and 290 Kelvin, and the turbine at 760 kilopascal and turbine inlet pressure is 760 kilopascal and temperature is 1100 Kelvin. Heat is transferred to air from an external source at a rate of 75 kilojoules per second. Determine the power delivered by this plant. So we have a compressor and we have a heat exchanger and we have a compression chamber connected to the turbine, and then this goes with this. This is 1, 2, 3, 4, 5, 6. We know T2 by T1 is P2 by P1 power gamma minus 1 by gamma. P2 by P1 is 760 kilopascal divided by 95 whole power 0.4 by 0.4. So T1 is known as 290 Kelvin. So this is 525.3 Kelvin. This is the compressor outlet temperature, and similarly we know that the turbine inlet temperature is 1100 Kelvin, and we can also assume the same pressure ratio, that is T T4 by T5 is equal to T4 by T5 whole power gamma minus 1 by gamma. So here T4 is 1100 Kelvin by T5 is equal to the pressure ratio, which is 760 by 95 whole power 0.4 by 1.4. That T5 is 1100 divided by 760 by 95 whole power 0.4 by 1.4. So this is 607.25 Kelvin. So we need to find the power output of the plant. For the power output, we know the rate at which the heat energy is coming in, and Now that we also know the work output for every kg of the working fluid, that can be calculated by enthalpy difference in the compressor and turbine. Now to find the uh, enthalpy inlet of the combustion chamber, we need to calculate T3. So since the effectiveness is 100%, we know that T3 is same as T6. So effectiveness equal to 100, so this implies T3 is equal to T6. We can calculate the compression work, so that is H2 minus H1, which is Cp into T2 minus T1. This is 1.005 into T2 is 525.3 Kelvin minus T1. T1 is 290 Kelvin. So this is 236.47 kilojoule per kg. Similarly, for the turbine work we have H4 minus H5. Here so this is 1.005 into T4 minus T5. So T5 is known. T4 is also given, that is 1100 Kelvin minus T5 is 607.25 Kelvin. This is 494.94 kilojoule per kg. So net work output is T turbine, work turbine minus work compression, which is 494.94 minus compression work, which is 236.47. This is 258.47 kilojoule per kg. Now we have calculated the work transfer, but work output of the gas turbine, but we still not sure how to get the T3 value or the enthalpy at 3. Q in is H4 minus H3. And from Q heat exchanger we know T5 minus T6 is equal to T5 minus T6 is equal to T3 minus sorry, H3 minus H2. Here we know that H3 and H6 are same, and only 2 and 5 is also known. So then writing this in terms of temperature, we have T5 minus T6 is equal to T3 minus T2. So here this T3 and then this will become 2T3 is equal to T5 plus T2. So T3 is T5 plus T2 by 2. T5 is 607.25 and T2 is 525.3 Kelvin. 4 by 2. So this is 566.275 Kelvin. Now we can find Q in, which is Cp into T4 minus T3, which is 1.005 into T4 is 1100 minus T3 is 566.275. So this is 536.4 kilojoule per kg. We know that Q dot is given as 75,000 kilojoules per second. So that is 75,000 into 10 power 3 kilojoules per second is given in, and we need to calculate the work output. We know the cycle efficiency, which is work by Qn. So here work is 258.47 and Qn is 536.4. This is 48.19%. That means the work power output will be 0.4819 times 75 into 10 power 3 kilojoule per second. So that is 36,139 kilojoule per second. So this is 36.14 megawatt. In this problem, we have considered the specific heat of the air is at we assume that the specific heat of air is throughout the constant and the value is taken for the value of room temperature, which is 1.005, but in actual the specific heat also changes with temperature, and that is a second part of the problem where we want to account for the variation in specific heat with temperature. So for such problems, a steam table, or sorry, gas property table should be given. So here okay, ideal gas properties of air table is so for such problems, it is generally we should take the temperature here. I mean, when there is a temperature and you want to calculate the enthalpy at a particular temperature, instead of just multiplying with the Cp, we should go to the table and find the enthalpy for the particular temperature. So here the temperature steps are given in 5 degrees, 5 Kelvin at this region, bottom region around 310 and 315, but initially there is a step of 10 Kelvin. Anyway, we can, for any intermediate value, we have to interpolate and then find the enthalpy. So the problem can be again found by using this enthalpy values. If you have any questions with this problem, you can ask now. Otherwise, I have one more problem to solve. Yes. Okay, I will move on to the next problem. Air enters a compressor of a regenerative gas turbine engine at 300 Kelvin and 100 kilopascal, where it is compressed to 800 kilopascal and 580 Kelvin. The regenerative generator has an effectiveness of 72%, and the air enters the turbine at 1200 Kelvin. For a turbine efficiency of 86%, determine the amount of heat transfer in the regenerator and the thermal efficiency. Assume variable specific heat for air. Okay, so here they have asked to use variable specific heat, but I would solve with a constant heat, constant specific heat. So initially air enters the compressor at P1, state 1. It is 100 kilopascal, and T1 is 300 Kelvin, and then there is a regenerator, and after that we have the combustion chamber, and then we have turbine. So this state is 2, this is 3, 4, and then we have a turbine. Expand the gas and it goes out state 5, and after the regenerator, the air escapes to the atmosphere at state 6. Now we know P1 T1 is given. After compression, the pressure becomes 800 kilopascal, and the temperature is also given as 580 Kelvin. The effectiveness of the regenerator is given as 0.72 or 72%, which means that T5 minus T6 divided by T5 minus T2 is 0.72, and the air enters the turbine at 1200 Kelvin. That is T4 is 1200 Kelvin, and the turbine efficiency is given as 86%, which is 0.86, and you can determine the amount of heat generator, heat transfer, and the thermal efficiency. So state 2 is given, and state 3 is unknown, but state 4 is known. With state 4 we can calculate state 5. So we know T5 by T4 by T5 is P4 by P5 power gamma minus 1 by gamma. This is T4 is 1200 Kelvin by T5 is unknown. P4 by P5 is 800 by 100 divided power 1.4 by 1.4. Now T5 is 1200 divided by 8 power 0.4 by 1.4. This is 662.45 Kelvin. Now we have this effectiveness is 0.72. This is T5 minus T6. So this is 662.45 minus T6 is unknown, and again T5 is 662.45 minus T2, which is 580. This T6 can be computed, which is 662.45 minus 0.72 into 662.45 minus 580. This is 662.45. This is 603.041 Kelvin. So heat transfer from the heat exchanger is Cp into T5 minus T6, that is 1.005 into T5 is 662.45 minus T6 is 603.1. That is 59.6 kilojoule per kg of the working fluid. So the amount of heat transferred in the regenerator is found. Now we can calculate the thermal efficiency. So for thermal efficiency, we want work output from the turbine and compressor. For the compressor work is the H2 minus H1, which is Cp into T2 minus T1. Similarly, turbine work is H4 minus H5, which is T4 minus T5. So compressor we have 1.005 into T2 is 580 minus T1 is 300. Similarly, for the turbine work we have 1.005 into T4 is given as 1200 Kelvin minus T5 is 662.45. This is 281.4. I think in this problem I haven't used this turbine efficiency, but I think we have seen how to use it earlier, and it is not so difficult to use. This is 540.2 kilojoule per kg. Now we know the net work output, which is turbine work minus compressor work, which is 540.2 minus 281.4. This is 258.8 kilojoule per kg. Similarly, heat input can be calculated as H4 minus H3, which is Cp into T4 minus T3, which is 1.005 into T4 is 1200 Kelvin, and T3 is not computed, so from T6 we will be able to calculate T3. Q heat transfer equal to H5 minus H6 on the one side, and on the other side it is H3 minus H2. So here in writing in terms of temperature we have T5 minus T6 equal to T3 minus T2. So T3 is equal to T2 plus T5 minus T6, which is T2 is 580 Kelvin, T5 is 662.45 minus T6 is 603.1. So it is 639.35 Kelvin. This way we can compute the heat input. So this is 563.45 kilojoule per kg. Calculating the cycle efficiency, we have W by Qin, which is W is 258.8 divided by heat energy input is 563.45. This is 45.93%. The actual answers are varied because one is because I didn't use turbine efficiency of 86%, and also I didn't use the variable specific heat. So this is something you can try and ask me in the next class if I have any problem with this. You have any questions with the problem, or we can meet in the next session. Okay, if there are no problems, I will close the session. Thank you for attending.